Hello, everyone. Thanks, everyone, for being here. We really appreciate for those of you who stick to the end and be patient with us. And also, thank you, Scott, for giving us this wonderful opportunity. And all right, here we go. So today we're going to be talking about Markov chain matchup model with multivariable approach. My name is Jeff Chin. I am a recent graduate from the Master of Sports Business program at NYU. And this is my colleague, Chris Chen. And he's an undergraduate data science major from NYU as well. So, but we first have to apologize in advance that we didn't prepare any fancy hooks to get your attention. So there you go. Yeah. So our research is inspired by another fellow student a couple of years earlier, Connor Turner, who presented his research on the topic of Markov chain as well. Specifically Markov chain matchup models to simulate baseball balls and strike counts for the entire matchup. And we think that is a very interesting approach. And specifically, even though Markov chains is a very widely known, widely used method to simulate the entire game, however, for some reason, we haven't seen a lot of work being done on the Markov chain simulating and particular matchups. So yeah, so we think it's very interesting, and we wanted to test this out and see what validates this approach, and make any potential improvement on it. So first of all, we're gonna have to do this. We need to understand what is a Markov chain. So a Markov chain is simply a very simple mathematical process that represents the transitions from one state to another or one event to another. And in particular, on this chain of events or state, any future state is directly dependent on or only on the current state and not as much as the states that happened before. And this relationship is captured by this conditional probability expression down below here. And to give you an example illustration of how it works, so here we have Sandy Alcantara, the 2022 season National League Cy Young winner. And on the right here is basically the pitch arsenal of Alcantara. With that being said, we know that according to StatCast, he threw actually 5 pitches, but for simplicity reasons, we just combine the major ones. So obviously the purple circles represents the pitch types that he has thrown. And the gray arrows and the percentage numbers represents the transitional probability that Alcantara throws one pitch after the other. Specifically, for example, if it starts out by saying the throw a fastball, then there's a 51% chance that he's gonna throw another fastball right after. And then there's a 22% chance that he'll throw a slider, 27% chance for changeup. And if he starts out by throwing a slider, then the same story applies. But obviously the probabilities are slightly changed. Same goes for the changeup as well. So yeah. So it's good that we can know the probability of what type of pitch he'll throw based on the previous pitch, but how does that relate to analytics and Markov chain? So it turns out that we can. It turns out that we can represent this entire transition properties through a 2-dimensional matrix, and with that we can further infer all the possible probability distribution of all the future pitch that he throws at any given time in the future through a process called the Markov chain evolution. So this is just what I talked about, the transition matrix, which is exactly the same information as you've seen from that graph earlier, and all of these numbers are still the same. For example, this 0.22 represents that there's 22% chance that he'll throw a slider immediately after he throws a fastball. And we'll call this transition matrix T1, the initial transition matrix. So going through this Markov chain evolution, what we do is we simply multiply T1 and T1 together through a dot product operation, and we get T2, which is the second time step matrix. So, and at this point, you can already see that the probability is shifting a little bit. And what this graph, what this chart shows is that given that Alcantara throws, by the way, I'm talking about the one on the right, given that Alcantara throws one of these pitch types on the left here, the row headers, these numbers represents that probability he will throw the pitch types in the top for his third pitch. So this is the second time stat matrix. So the probabilities are referring to his third pitch, and we can do this continuously, on and on, and you'll see the probabilities changes furthermore. And this time, the third time steps matrix, the probability represents that for Alcantara's fourth pitch. So by the time we get to the 10th time steps matrix for this particular case, you'll notice a pattern that, first of all, these probabilities have essentially converged together. And this is what we call that we have reached a steady state matrix. And we can still perform this operation, furthermore, but these probability will essentially just stay the same, like forever. And what this tells us is that now, if Alcantara throw his first pitch on one of these pitches from the left, there is these numbers represent the probability that he will throw one of those pitches on the top for his 11th pitch. And that I think make intuitive sense, and especially when we circle back to my previous earlier points about a Markov chain. Any future state is not dependent on the states before, but only the current states. So another example is that imagine a plate appearance where Alcantara throws a 100 pitch. The probability that he throws a fastball on the 100 pitch has very little to do with what he threw on the first pitch, but have something to do with what he threw just one pitch right before. So now that we have a basic understanding of how Markov chain works, we'll bring Chris on to talk about Turner's approach.
Right. So now I'm going to talk about the Turner's approach, and let's go into it. So here we can see these are actually most of the possible events that can happen in an inning. So actually we're starting from 0-0 and go down to 1-0 or 0-1. And keep in mind that there's no way we can go back, or there's no way we can go horizontally, because due to the new nature of baseball. And at the end of each plate appearance, the final results will always come down to a walk, a strike, or all the events that happens on the left. And with that in mind, let's take a look at a real game example. Sorry. So here the pitch starts at 0-0 and end up with a strike. And here we can see that how these events actually chained to each other. And that's actually like the basic logic of Markov chain when we are simulating a pitch to pitch all the way until the plate appearance is over. And here's another example from between Mike Trout and Justin Verlander that end up with a field out. So with that in mind, and also plus that the data that we collected from StatCast from 2015 to 2019, we will be able to recreate this player transition matrix that have the actual count on the left and the actual player appearance event on the upper right side. And the P inside here represents the actual probability of these corresponding count when these events happened. And now if we have these two players transitional matrix, what Turner proposed is that we can actually sum them up together and get the average of them to predict their future outcome if these players were to play together. I'm sorry, to play against each other. And here is the matchup transitional matrix. What we do is, again, we take the dot product itself for 100 times in order to make the probability stable. And we drop all the zeros and ones because they are all used as repetitive information. And there we go. We get the matchup steady state matrix. And here is actually what represents the outcome when these players were to play with each other. And if you look at the first row, which is when the count is starting at 0-0, it looks like this. It's a probability distribution that sum up with 1, and it's the prediction that the Markov chain made when these players play with each other when it's the count 0-0.
All right. So this is basically Turner's proposal. We think it's very interesting, but our question is, how good is this approach? And we want to set up a test to using empirical data to test it out. So we gathered data from 2015 to 2019 StatCast pitch by pitch data, and we used 15 to 18 season to train to build the Markov chain model, and then use the 2019 season data for testing. And to avoid, a lot of players will have very limited sample size, which will give us sparse probabilities, which will throw off our predictions. So we had this cutoff point, 400 plate appearance minimum for batter, 500 for pitchers, and we're left at about 1,000 total players that we performed our test on. And so second thing is that we got to find some essentially error or accuracy measurement for these predictions. So we elected to use a Breyer score, which is a widely used measure for the accuracy of probabilistic predictions. And it's captured by this formula on the right, but essentially Breyer score is just pretty much exactly the same as the sum of squared errors. And that's the below table represents how it works. So we have all the true outcomes on the left, 3 events, for example, and we have 3 observations. And on the right, we have the predicted probabilities. And then we calculate each of the sum of squared errors for each observations, and we get the average from that. So that's our final Breyer score. And of course, the lower, the better. And to help you guys visualize how we set up the test, this is a sample of the 2019 test data that we use. All the and we essentially did the same on that we did for the last slides, and we calculated that the average Breyer score that we get from the 2019 test data is 0.7016. So not that we have a baseline of this error, but what does it mean actually? Like, how good is this number? So to find that out, we went out to create some other models, benchmark models for comparison. One of which is the standardized log5 model, which is also widely used benchmark model to predict the outcome of a plate appearance. And as you can see, the Turner's benchmark model is pretty much on par of the log5 model, and perhaps slightly worse. We also did a pitcher average model, which is using the pitcher's average transition matrix or his plate appearance outcome probability distribution from his historical data against the entire league. And we also did the same with the batter's average and also the league average, and a random prediction test at the end. Here are the results on the right here. And so through that, hopefully we have established that the Markov chain matchup model has at least some validity, some predictive power. But now we wanted to figure out how to make this model better. So the first thing we want to tackle is that, as a lot of you might have already noticed, there is a big assumption that's been made from the benchmark model, which is that we're currently taking the average of the pitchers and the batters transition matrix and use that to predict their matchup transition, which is intuitively, makes a lot of sense. We're treating them as equal, but in reality, that might not be the case. And so we developed this new formula down below, which is a very, simple formula with, we're taking the pitcher transition matrix, apply a weight to it. The range is from 0 to 1. And then we add the batter's transition matrix and then apply a different, the same weight, but instead using 1 minus that pitcher weight. So to get the new matchup model. And essentially when that pitcher weight is equals to 0.5, that's essentially the same as the current method. So what we did next is we simply, run all the possible weights from 0 to 1, of course, at an increment. We found that the best pitcher's weight is around 0.34, and we got a slightly improved Breyer score of 0.7013.
And here's actually another approach that we use to try to improve our model predictions. And our presumption is that the player's performance is extremely time sensitive. A player in 2023 can be actually very different from what he is in 2021 or 2020. So we have to come up with a realistic way to try to reflect the player's true ability and put it in a numerical way to implement it in our model. So here's the weight function that we come up with. Here we take the number of years that it is as an input and a as a parameter to change the actual weight that we want it to be. And as you can see in the graph, this is actually like a graduate descent math function. And throughout our research, we found that the more aggressive weight it is, the better prediction result it will give us. But it's like in a fairly in a sense that it's a range that makes sense. I'm sorry. And the best score it gives us is 0.701. And the other approach that we use is adding the empirical matchup results. So here our pre-assumption is that the future matchup results can be reflected by the historical matchup results. So if there's a way that we can tell the model, okay, these players have been playing with each other. If we use the old results and tell the model, if the model can learn and see, it can predict better if these players were to play with each other. And here, for the number of matchups that's more than 10 times that happens in the season 2015 and 2018, there's actually 11,600 of them. And for them to be appeared in the season 2019 for at least one matchup, there's 3,600 of them. And there's only 1,100 of them for them to be appeared in 2019 for more than 5 matchups. And as we can see in the chart, the numbers actually decrease dramatically. When we go down to all the way to the bottom, for players that have been playing with each other for more than 50 matchups, there's only 10 of them, 10 pairs of them in the season 2015 and 2018, and only six of them appeared in 2019, and 3 of them appeared for more than 5 times. So this approach actually suffered from the extreme lack of data, and however, we do observe this minor decrease, which means that the prediction power actually increased when we use more than 40 matchups in the train set and more than 5 matchups in the test set. And we'll also detect this positive correlation between the number of matchups and model performance. So if in the future we have more data to be implemented in this model, I think the prediction outcome will actually be better.
All right. So we have tried all of these improvement to make the model better, and now we wanted to see if by way of combining machine learning approaches into it, if it's going to be better. So we found a way to combine machine learning algorithms with some elements of the Markov chain together and see what are the potential results. So machine learners are well versed for large and complex data sets, and it's widely used in sports analytics and analytics fields in general. So that's why we wanted to try it out. So here down below is are the procedures we took. So we first used the individual. So for each plate appearance or each matchup, we used the individual players transition matrix as the predictor variables. And then we performed a PCA dimension reduction technique to it before we fitted 3 different machine learning algorithms for comparisons. And just to help you guys visualize it a little better, here's another example between Verlander and Trout. And on the right is their individual transition matrix. And what we do next is that for every one of them, we strip out every single row. And then we removed all the zeros because those are the impossible transition, from 0, 0 to 0, 0 counts. So we removed them, and then we simply just concatenated all the probabilities together to make a giant row of features of their own individual transition probabilities. So we ended up having a total 194 predictors. And then we applied the principal component analysis to it because through trial and error and then through testing, we found that reducing the number of features down to about 20 will give us the slightly better results. So at the end, this is our final results after the implementing the machine learning approaches. So to our slight surprise, the refined Markov chain method is still the highest performing method out of all of these approaches followed closely by the log5 model, and then the benchmark Markov chain model. All of the machine learning approaches kind of hangs around after the pitchers and bit batters average, and then the random forest even performs slightly worse than the league averages. And we have some theories of why that is, but we would, for the sake of time, we would love to discuss them if there's any questions about them later on. So essentially, in summary, there are several findings from our research. First of all, which is that we think that Markov chain matchup model is definitely a valid approach. There are certainly a lot of things that we could do to improve it further on. And then the second thing is that is also slightly surprising is that the optimal pitcher weight is 0.34, which is for better prediction, we should weigh the batters more. Like to us, this is slightly controversial because we would think that the pitchers at least would take about half or maybe even more of the equation because they are the dominant, they are the proactive side of pitching and batting. And yeah, so this is slightly surprising to us. And the third one is that machine learning models performance was slightly suboptimal. And again, for the sake of time, we would love to talk about it later. Yeah, so just in terms of future development, obviously we wanted to definitely incorporate more, additional data, and that will allow us to include more empirical matchup results, which could potentially improve this model. And then we will also would like to examine the specific interactions between pitchers and batters, because at this point, all of our models essentially just look at the past historical data from the pitcher and the batter individually against the league, use that as the foundation for our analysis, which is obviously we're missing a lot of unique characteristics between a specific batter and pitcher. And if we can capture those, that will hopefully make the model better. And lastly, of course, we would want to deploy more versatile, machine learning methods that could potentially capture the very complex relationship between these transition matrix, transition probabilities, for example, neural networks, and then see how that and then see what it will do. So yeah, with that, that's the end of our presentation. Thank you very much for listening. Feel free to reach out to us from this email address, and then our code base is currently stored at this GitHub address, but feel free to check it out. But it's currently very messy right now, so please give us like a 2 weeks or so to clean it up, to make it presentable. Yeah, so yeah, with that, thank you so much. Yeah, thank you. Yeah, by the way, we're open to any questions if you have any. Yeah, here. Yeah, sure.
Previous seasons, and so I'm sort of guessing what you're saying is that how well you expect somebody to get at the end of 2020 might be partly based not only on what it did in 2020, but what it did in 2019 and 2018 and 2017.
Yeah, so the Markov chain structure that we build it upon is not particularly based on season by season, but through count by count. So if we go back to this slide here, okay. Yeah, so this is essentially the Markov chain itself. So any one of this count will be essentially a state. We started with 0, 0, and there's a probability that it was transitioned into 1, 0, which is a ball. And then there's another, after that, there's a probability it will transition into 1, 1. So yeah, so one of these chains, highlighted in dark purple will be considered one of our Markov chain. Yeah, the year season, variability you're talking about is a later step where we applied individual weights to each year to, capture the player's most recent performance, due to, aging and all that stuff. Yeah. Thank you for your question. Here.
Did you consider using separate probabilities for considerations like
Verlander versus a right-handed batter, Verlander versus a left-handed batter, or Trout versus a left-handed pitcher, Trout versus a right-handed pitcher? Because I wonder if that would pull out a little more accuracy in the outcomes for the, because we're just, it has a
Yeah.
huge difference out of it.
Great question. Unfortunately, we did not, and we actually just simply due to time restrictions, we actually did try to incorporate platoon effect and other external variables like power factors in our machine learning approaches early on. But there's we went into some problem with the methodologies of which we implemented it, and so we didn't choose to like present that. But that's definitely something we'll probably improve this model. Yep, here.
Consider a more detailed decision tree. For example, each pitch, the batter has to decide to take or swing. If he takes, it could be hit by pitch, called strike, and called ball. If he swings, the swing or miss, foul, or it's fair. If it's fair, is it over the fence? If it's in play, is the batter, is it in the house? If not, then the batter stop the first, stop the second, stop the third, which come on the fourth.
Yeah, that's totally, we think that's totally viable, and all these different Markov chain structures. We talked about how other research are primarily using they're primarily using the R24, the base out situation, as the foundation state to simulate the entire game. But for now, we're just using the count. But I think what you just mentioned is totally doable in the future. I think yeah, that could be a valid approach. Please.
I may just misunderstand something. They go over my head, but what constitutes a predictive failure and what constitutes a predictive success in your test? And what kind of specific things count as failures? And what counts as successes?
Yes, great question. So if we go to this slides with our, where's no, sorry, it's after that. Yes, we go to this slide. So eventually our prediction is just this one, probability distribution that predicts all of this pitcher and batter matchup pairs future performance. So, it doesn't matter how many times they play in the future, we'll always predict the same. Our best hope is that this probability distribution will capitalize all the future event frequencies. So we're hoping that Mike Trout will always hit 13% of singles. If we're talking every individual predictions, then obviously it's not going to be very close to 100% accuracy, because there's just no way that we accurately predict, hey, for this particular play appearance, it's going to be a home run. But we're hoping to predict the long-term tendency of those matchups. Yep. All right. I think that's it for us. All right. Thank you. Thank you, guys. Thanks again.
Well, and that's a wrap. I'd really like to once again thank all of our panelists and presenters from the last 3 days. Really was great to see everyone back in person. We also, I mentioned at the top, we're in a new venue this year. If you got any feedback about the venue, definitely want to hear about that. SABR's really proud to be able to host this event, and want to thank all the folks from throughout the industry who support us and help us make this conference a reality every year. Please do stay tuned to your email over the next few weeks about dates for the 2024 conference. And thanks again. We'll see you next year.